So next, excited to hear more from Richelle van Capelleveen about the WISPIT survey and some of the interesting discoveries.
Thank you. Good morning, everyone. I'm Richelle van Capelleveen, and I'm a third-year PhD candidate at Leiden Observatory. I work with the Wide Separation Planets in Time survey, and today I'm excited to share some of the first results of this with you, as well as some preliminary takeaways. So I'll just dive right into how this survey started, and that is with this figure that I think you've seen it many times this week. So if you look at this figure, you see that most of the directly imaged planets are at separations more than 50 AU, and many of them are at separations even more than 100 AU. So this immediately gives us a question of how did these planets get there? Because it's unlikely that they formed at such wide separations through core accretion, simply because the timescale required to form a planet at that separation through core accretion, that takes too long compared to the typical disk lifetime. So if it's not through that mechanism, how did these planets get there? So we're thinking about, did they scatter to such wide separations, or did they form in situ through other formation mechanisms? So the WISPIT survey was designed to help answer this question. A little bit about how the survey, how the targets in the survey were selected. So we started with the SARI catalog. This is a catalog of stars younger than 20 million years old, within 500 parsec, selected based on Gaia 2. But this is a huge catalog. This is some 40,000 stars, so we made the selection a bit smaller. We selected stars based on mass to only get solar mass stars. And then, since this survey is like the WISES survey, so a snapshot survey with the first observation of a star and then another observation a year later, we selected stars with a proper motion higher than 10 milliarc seconds per year, with the idea that if you have these two observations, you can distinguish what is a background source and what is a bound companion. Then, of course, after this, also some further selections to make sure that it's actually observable from the VLT. So magnitude brighter than 14 for AO log, and of course the position on the sky. So this is what it looks like if you plot the survey targets in a figure. So we're at the center of this figure. In blue, you see all of the targets from the SARI catalog in a density plot. And as these are younger than 20 million years, it's not a surprise that the higher overdensities can be identified as some of the known young star-forming associations. The WISPIT survey targets in pink are then also, not surprisingly, mostly in these clusters, but not exclusively. So you do see that many of them are also in the outskirts of these regions, or some of them are field stars. The current status of this survey is that all of the targets have already had their first observation, and about 44% has had their second observation already. Most of the targets are being observed right now, because observing block B116 is happening now. So we're hoping that at the end of this block, the survey will be about 95% complete. So looking at this first bit of the survey, what did we find so far? And I think many of you may have already seen the WISPIT2 system, but we didn't just start counting at 2. There really is also a WISPIT1 system. So this is it. WISPIT1 is approximately 15.5 million years old, and it has 2 bound companions. Now, the big surprise with this system is when we looked at the flux calibration image, it's not a nice round PSF, and it turned out that this can be modeled really quite nosely by a binary with a solar type primary and an M-dwarf secondary, and then those are at a separation of approximately 10.5 AU. This is particularly funny after the previous talk, because when we wanted to find the mass of the planets, of all of the many models we could choose, we selected the models that are too old to use. But from these models, we're getting a mass for WISPIT1b of approximately 10 Jupiter masses. It's at a physical separation of 330 AU. And for the second companion, a mass of approximately 5 Jupiter masses, and it's at a separation of 840 AU. So these separations are really quite wide, and that makes this system among the widest separation directly imaged planets to date. So now for the system that you have seen, but probably not this figure a lot, is the WISPIT 2 system. And I thought it'd just be funny, because I have some time, to tell you how we went from this to the images that you all have seen, because it almost didn't happen. So in the first year of my PhD, I was working on planet collisions, and I didn't really start working on the WISPIT survey until I think it was September, early October 2024. And the WISPIT survey is being resubmitted every block. It's not like a one large program, but lots of separated observations. So the thing I started with is just redoing all the bookkeeping. And it turns out that some 9 targets that were supposed to be observed weren't going to be observed. So we needed to do some very last-minute target change requests. And I think that the second observation of this target was also in there. But mostly the observing block had already started. I had never worked with the phase 2 system of ESO. So a collaborator of ours, Christian Ginsky, he helped me, and he put in these OBs in a new system for us. So if it weren't for him helping us with that, maybe this wouldn't have been observed. So that's already part 1. But yeah, so he did this work for us. Then a few weeks later, we got these images of a disk. Now, I already had plenty of projects to work on. So Matt wasn't really necessarily loving this a lot. I think when he saw a disk, he just saw a massive time sink for me. But Christian Ginsky, he really loves this. He was super excited about this. So he sent us an email like, oh, you should really observe this in polarimetry. This is awesome. And yeah, his excitement really caught on. And also I thought, well, he's been doing a lot of work for us with these OBs. He's helped us. This would make him very happy. So you know what? Why not? I'll swap out some 2 more WISPIT survey targets for a long polarimetry observation. Turned out to be a really good choice, because this is the polarimetry observation that we ended up getting. So this shows the WISPIT 2 system, 5 million-year-old star. And when observed in polarized light, you can clearly see these 4 different rings, and a disk that is detected out to at least 380 AU. Now, when we got this image, the whole team did agree that we definitely wanted to observe this some more. So we also reached out to the MEGIOX team. And it turns out that there is an accreting planet in gap 3. So you can see it in this figure here. This planet has been detected both in H alpha, also shout out to the MEGIOX team, and in H and KS bands with VLT sphere. Again, these models. So turns out the planet is approximately 5 Jupiter masses, and it's at a separation of 57 AU. What was nice is once we knew where to look for the planet, we could retrieve it from our very first observations as well, which gave us astrometric measurements over a period of approximately 1.5 years. And it turns out that, well, with only these measurements, if you limit it to only allowing orbits within the gap, then these measurements are consistent with various orbits of the planet in the gap, which makes this system the very first system with a gap-carving planet that can then be really used in the future for planet-disk interaction models. So speaking of planet-disk interaction models, I just wanted to highlight the contribution of the team of Christian Ginsky, because they've done all of these planet-disk interaction for our paper. But then, of course, this is only the University of Galway site. And as you can see, they had these really nice pictures taken for their press release, but we did not. So, yeah, but I mean, I made it work because I wanted to make this large group picture, so I just chose the most suitable picture of my supervisor and I to... So this was not the end of the whole WISPIT 2 story, because this blob closer in, I'm going to see if I can, yeah. That blob closer in that was identified in the paper by Laird Close as well. It turns out to be a real planet. If we take a bit of a closer look, this is the total intensity image of our very first polarimetry observation. And this is really close in, because it's on a 50% transmission of the coronagraph. And so if you look at this and you think, well, is this not just maybe a really persistent speckle? The confirmation of this, which is in a paper submitted by Chloe Lawler, is based on a very nice gravity spectrum. But I'm not going to show you the spectrum here. If you want to see the spectrum, please go and see her poster and poster number 47. So to summarize the results of the WISPIT survey, and what was surprising to us at first is that WISPIT 1 is a binary. And second, even though most of our survey targets are inside these known young associations, both WISPIT 1 and WISPIT 2 are not part of any of these known young associations. So what I want you to take away from this, and this is something that I also would want to be working on in the final 1.5 years of my PhD, is to think about what we should include in direct imaging surveys in the future. Because so far, quite often binaries are explicitly excluded from surveys, even though we found some really interesting targets. And then not just WISPIT 1, but earlier this week, also mentions of DeLorme1 and SR12. So we should really include binaries in direct imaging surveys in the future. And then secondly, I think the reason that WISPIT 2 has gone unnoticed for so long is because it's not part of a cluster. So for the future, we should really make sure to also include field stars in direct imaging surveys when we're looking for both planets and specifically also embedded planets.
Hi, Carl Stoppelfeld from JPL. Really great results. I'm curious about how this fits in with disk evolution. The WISPIT target sample, you say it's 178. What's the distribution of disk luminosities across that sample? Are you looking primarily at protoplanetary disks, young debris disks, or something in between?
Well, so this is easy to answer in the sense that WISPIT 2 is literally the only disk in this sample. So the survey wasn't designed to find embedded planets. It was designed to find systems from the youngest ages of gravitational instability, so approximately like 500,000 years old, to the older stages of where a planet could have been scattered outwards. And so it's not unexpected to have a disk in there because we selected young systems, but we didn't on purpose want to select disks. So it just happened to be in the survey in that sense. And of course, once we did see this, we went through all the other images to see if there might be any other clear disks in there, but there weren't. At least not from what we could see with just the broadband H and broadband K images.
Hi, Tiffany Meshcott. Oh, can you hear me? Hi, IPAC Caltech. Great talk, thank you. My question is, you opened with talking about understanding core accretion versus gravitational instability in these really wide separated planets. So can you comment on that for these two detections?
I think I have a lot of extra slides, let's see.
I didn't realize that.
Yeah, wait, was it this one? No? I've given this presentation in many different versions. Okay, yeah, so the idea of how to answer the question is to compare simulations to observations. So this is why we chose a large sample and then you eliminate other parameters, which is why only solar mass stars. Also, at the time of the survey, there was a gap in planets observed around solar type stars. So that kind of made this the perfect type of star to look around. So I think if core accretion were to be the dominant formation mechanism, you would expect a slightly higher detection rate of widely separated planets. So that would be the one part of answering this question. So just compare the survey statistics to what you would expect from simulations. And then, of course, any of the targets that you do find can be analyzed and characterized. And the chemistry of these planets might also help answer some questions about how they were formed.
Yeah, I'm interested in the dynamics of the WISPIT 1 system, because those planets are so far out that it would be hard to form them there. But it's not intuitive to me that you would be able to migrate 2 planets out without ejecting anything. Are you thinking about the dynamics of that system more, and do you have any more that you could say on that?
Yeah, so it's also interesting because WISPIT 1b and WISPIT 1c are Different in the sense that you might also wonder if maybe they had different formation mechanisms, so 1b and 1c not formed exactly in the same way. So 1c is so far out that even through gravitational instability, forming a planet at 800 AU, that's so far that there has to be some sort of scattering involved, is what I would think. But then you would want to follow up on these planets, because if they were to have, for example, a circumplanetary disk, then that would make scattering less likely, because how would you retain a CPD after sort of violently scattering a planet out to a further orbit? So a lot of discussion can be done on what we would think might be the more reasonable formation mechanism, but you really do need follow-ups on both of these planets to eliminate some of the options.